This is section 5.4, Exponential Functions, Differentiation and Integration. Now, first of all, let's review what we know about the natural logarithm function, commonly referred to as ln of x. Not something you mow. Please don't say something that sounds like you're going to mow it. It's ln of x, or natural logarithm of x. Anyway, the natural logarithm graph is always increasing in concave down, and that's 1. And the graph looks like this. Passes through the x-axis at 1, is asymptotic to the negative y-axis. It's always increasing in concave down. Looks like that. Okay. Since it's monotonic and it's 1-to-1, because it passes both the vertical line test and the horizontal line test, then it has an inverse. And what we know about the inverse is that it will be a reflection of this graph over the line y equals x. And so the point 1, 0 will become 0, 1. And whereas the function is asymptotic to the negative y-axis, its inverse will be asymptotic to the negative x-axis. The graph will be increasing. One of the things we talked about in the last section is if a function is increasing, its inverse will be increasing. So this function is always increasing, and it's the reflection of the green one over the line y equals x. So it's going to look like that. So this is our inverse function graph. So I forgot to write the negative 1. Okay. So as it turns out, the graph that looks like that is e to the x, and that is its inverse function. Okay. We could have solved for that. Let me do that really quickly. If we'd started with y equals ln of x, which of course is log base e of x, in case you forget. Okay, then the inverse is going to be change every y into an x and every x into a y, then solve for y. And to solve for y, what I'm going to use is the exponentiation of both sides of the equation as a power of e. So that's going to be the new thing we're introducing, is that we're making the left side the exponent of e and the right side the exponent of e. And of course, anytime the base of the power, here e, is the same as the base of the logarithm, here e, since they're the same, you get back the argument of that logarithm, and it's just y. And so that means that our inverse function for ln of x is e to the x. Sort of the algebraic proof of it. So, because they're inverses, f of f inverse of x is supposed to be x. So what that means is that the natural logarithm of e to the x is just simply x. And because they're inverses, the composition the other way, the composition of f inverse of f of x, should also be x. And so here that's e to the ln of x which is x. Okay. And that leads us to the connection between the ln of x and e to the x. They are definitely inverse functions. So if we go to the definition of natural exponential function, the inverse function of the natural logarithmic function, f of x equals ln of x, is called the natural exponential function. That's the name of this function that we just talked about. We call it the inverse. F inverse of x will be e to the x if f of x is ln of x. And what that leads us to is something called the definition. The definition is something that says, and this is a kind of a key idea, that especially in college algebra and maybe pre-calculus if you get to it, is that y equals e to the x if and only if x equals the ln of y. They call this the definition of logarithm, of the natural logarithm. So you'd want to memorize these two things. The if and only if means that if y equals e to the x, then that means x has to be ln of y. It also means that if x is ln of y, that necessarily y will have to be e to the x. It's a two-way street. That's what if and only if implies. Is that given one, the other one has to be true. So that's what we call the definition of the natural logarithm in the exponential function. I'm sorry. So let's use that idea to solve an equation. That's what this definition is good for. If 7 is e to the x plus 1, and you're supposed to solve for x, then you could take the natural logarithm of both sides of the equation. And that's a good thing, because when you take the ln of e to any power, because they're inverses, the answer is just whatever that power is, whatever that exponent is. And so subtracting 1 from both sides means that x is natural log of 7 minus 1. Okay, and if you put that in your calculator, if you really want a decimal approximation, or if you're asked for that in the homework, you should be able to type that into your calculator, of course, and check that out. Make sure you get this answer. And of course, the other thing you can do is substitute that into the original equation on the right and calculate what e to the 1.946, etc. is, and it should be exactly 7. Exactly, I say, if you use the calculator number instead of typing 0.946. If you type in 0.946, the answer won't be exactly 7, most likely, but it will be very close to 7, either 6.9992 or something, or 7.000001 or whatever. So anyway, it's something that you can check, and it's not that hard. So all of the rules that you learned about powers apply here. So if you have an exponential function, if a and b are real numbers, then if you are multiplying powers with the same base, even if it's e, you keep the base and add the exponents. So that rule doesn't change just because the base is e, transcendental number e. And the ratio or quotient of two powers of e, keep the base and subtract the exponents. The good news is stuff that we learned before is still true, and that's comforting. So if you look at the next page, it has a nice little table there. An inverse function f inverse shares many properties with the function f. So the natural exponential function inherits the properties listed below from the natural logarithmic function. The domain of e to the x is negative infinity to infinity. So if you look up at the graph up there at the beginning, the one in pink, that's the one we're looking at. The domain is all real numbers. The range is from 0 to infinity, not including 0. The function f of x equals e to the x is continuous. It is increasing, and it is one-to-one on its entire domain. This graph is concave upward on its entire domain. The concave downward graph, when reflected over the line y equals x, becomes concave upward. The limit as x approaches negative infinity, so as the pink graph goes off to the left, e to the x, the limit as x approaches negative infinity heads toward y equals 0. So the limit of e to the x as x approaches negative infinity is 0. And as you go off to the right, the pink graph, the limit of e to the x as x approaches infinity is infinity. The y values on the right just increasing without bound. Okay, one of the most intriguing and useful characteristics of the natural exponential function is that it is its own derivative. This is the only function for which this is true. And that's why I call this the coolest function ever. You may hear me say that like 6,000 times. It is the only non-trivial function. The trivial function is y equals 0. The derivative of 0 is 0. So it's, that's trivial. But this is a non-trivial function whose derivative is itself. Wow. Wow. There's no other function that does that. X squared's derivative is 2x, not the same function. The derivative of sine of x is cosine of x, not the same function. Now, of course, the chain rule version of this, we do have to pay attention to this. The chain rule is still in effect. So if you have e to the power of something that has x in it, let's generically call that e to the u, then you'll get back that same function, e to the u, still coolest function ever, but then the chain rule comes into play, and you then have to multiply that answer by the derivative of the inside function. Here, I'm calling that du dx. So don't forget that this is the coolest function ever. It's its own derivative, and then do pay attention to the chain rule. All right, so let's do a few examples with that. You're going to find that these are not that bad. This is a pretty easy problem to do. E to the 2x minus 1, we're supposed to take the derivative of that with respect to x. So since it's e to the something, we get that same something back. And then we multiply that answer by the derivative of the exponent. And the derivative of 2x minus 1 is 2. And generally speaking, we'll want to have constants written in front of powers. So this is the order in which you'd want to write the final answer. Okay, b, the derivative with respect to x of e to the negative 3 over x. Coolest function ever. You get back what you started with times the derivative of the inside function. And here the inside function is the exponent. So I'm going to go over here to the side and do a little bit of side work. Negative 3 over x. That's not a good form for taking the derivative. I don't like variables in the denominator if I can help it. So I'm going to rewrite that as the derivative of negative 3 times x to the negative first. And so the derivative is negative 3 times negative 1 is positive 3, x to the reduced by 1 power, negative 2, which we could write as 3 over x squared. So taking that back to our problem, this answer could be written as 3e to the negative 3 over x, all divided by x squared. part C. Of course, I think the chain rule part of this is probably the most difficult part because otherwise this is like a no-brainer, easy peasy. All right, so whenever we have products, the product rule and the quotient rule also as well, and any other rule we've talked about for derivatives will come into play. So this is the product of two functions. The derivative is the first function times the derivative of the second. The derivative of e to the x, coolest function ever, is itself e to the x, plus, that was first times derivative of the second, plus the second function times the derivative of the first one. And then you'd write that as x squared e to the x plus 2x e to the x. And because what we do with derivatives a lot of times is to set it equal to 0 to find critical numbers, or set it or say when does it fail to exist. A lot of times I will ask you to go ahead and factor, although that last line is a good answer. There's nothing wrong with it. You might be asked to factor. So there's a common factor of x and the common factor of e to the x. So when you divide x squared e to the x by our common factor, you're left with the other x, plus when you divide 2x e to the x by our common factor, you're left with 2. Okay, so that's a good form for the derivative, because if we were to set that equal to 0, we very easily see that x could be 0 or x could be negative 2. It'd be really quickly seen. Okay, so question D. What is the derivative of e to the 3x divided by e to the x plus 1? Okay, this is a quotient, so I'm going to use the quotient rule. So the quotient rule says low d high, the derivative of e to the 3x, coolest function ever, is itself e to the 3x times the derivative of the exponent, which is the inside function because of the chain rule, times 3. So that's low d high minus high e to the 3x d low, and the derivative of e to the x plus 1 is simply e to the x, because e to the x is the coolest function ever. Almost sounded like a Valley Girl there. Maybe that's too old of a reference for you guys. Anyway, low d high minus high d low all over the square of low. All right, so the common factor that I see is e to the 3x. So from the first group of things, if I factor that out, I'm left with 3 times e to the x plus 1 minus, and if I factor e to the 3x out from the second group, I'm left with e to the x all over e to the x plus 1. And we are leaving squared, I'm sorry. We are leaving this in factored form in the denominator because, of course, that would be easy to try to figure out if that's ever equal to 0 so that the derivative doesn't exist. So leaving it in factored form there is a good idea. Now, inside of those brackets, distributing the 3, that's 3 e to the x plus 3 minus e to the x. So the part of that I'm concerned with is 3e to the x minus 1e to the x is 2e to the x, then plus 1. I don't see any common factor in the numerator and denominator that I could cancel, so this is my final answer. That's that one. All right, now that we've established the derivative rule, that if we have the basic exponential function e to the x, that its derivative, because it's the coolest function ever, is e to the x. And so the antiderivative rule is very much related to that. If we take the answer to that and anti-differentiate it, we should get back what we took the derivative of, plus the constant of integration. So again, this is the coolest function ever, because not only is it its own derivative, it's its own antiderivative, plus c. Don't forget that part. So coolest function ever. And the u substitution version of that is e to the something, we'll call that something u, times the derivative of that something, we'll call that du, will give us back e to the u plus c. And that's really a very nice result. This is one of the easiest derivatives and antiderivatives that we will encounter. All right, so let's do one example with the antidifferentiation piece of this. So if I had, for example, the integral of e to the 3x plus 1 dx, I would let u equal the exponent on e, then find the derivative of u du, which is the derivative of 3x plus 1, which is 3, multiplied by dx. So I've got to have all of that du stuff. I have the dx, of course it's critical. I've got that. The only thing I'm missing is the 3, so I'm going to multiply inside by 3 and outside by 1/3. So in essence, I've multiplied both sides by, I've multiplied the problem by 1. So now I have the 3 I need, and so I'll have 1/3 integral of e to the now u, and the underlying stuff becomes du, and the antiderivative of e to the u du, coolest function ever, is e to the u plus c. Of course, that e to the u is multiplied by the constant 1/3 that we interjected to make us able to do this problem, because we needed the du to match. And then going back to the original variable, that'll be 1/3 e to the 3x plus 1 plus the constant of integration, c. And that ends this lesson. I'll see you in class.